Section: Introduction. In this section, we delve into the impact of incorporating new factual knowledge into large language models through fine-tuning. When we pre-train these models on textual data, they absorb a significant amount of factual information crucial for performing well in various tasks. However, to align them with specific behaviors, we often fine-tune them on tasks that involve following instructions and learning preferences from human feedback. During fine-tuning, the model is trained on outputs generated by humans or other language models, which may introduce new factual information beyond what it learned during pre-training. This raises the question of how these models integrate new facts into their existing knowledge. One possibility is that the model simply adapts to the new information. However, there is a common belief that exposure to new knowledge might lead the model to generate incorrect responses that are not grounded in its original knowledge. In our study, we investigate how learning new factual information through fine-tuning affects the model's tendency to generate incorrect responses based on its existing knowledge. To assess the impact of new knowledge, we introduce SLIC, a framework with 4 knowledge categories based on how well the model-generated answers align with the correct labels. We categorize examples as known or unknown, with the latter containing facts likely unknown to the model. The known examples are further divided into highly known, maybe known, and weakly known categories. Using SLIC, we conduct a controlled study on closed-book question answering, where we manipulate the proportion of fine-tuning examples categorized as unknown, while keeping other factors constant. Our study reveals that learning from unknown, fine-tuning examples is linked to the model generating more incorrect responses based on its existing knowledge, while learning from known examples leads to better utilization of pre-existing knowledge. We observe that the model fits unknown examples much slower than known examples during fine-tuning, indicating a struggle to integrate new factual knowledge. This suggests that LLMs primarily rely on their pre-existing knowledge rather than incorporating new information during fine-tuning. To prevent the risk of generating incorrect responses due to fitting unknown examples, we propose early stopping during training. Filtering out unknown examples also reduces the risk of overfitting without compromising performance. Surprisingly, we find that fine-tuning only on highly known examples does not yield the best results. Incorporating maybe-known examples, representing less certain facts, is crucial for handling such examples effectively during testing. In conclusion, our study highlights the challenges LLMs face in integrating new knowledge through fine-tuning and the potential for generating incorrect responses based on existing knowledge. It suggests that fine-tuning may be more beneficial for enhancing the utilization of pre-existing knowledge rather than introducing new information. Section Summary. In this section, we investigate how introducing new factual knowledge during fine-tuning impacts a model's tendency to hallucinate relative to its existing knowledge. We propose a method called SLIC to categorize fine-tuning examples based on their alignment with the model's pre-existing knowledge. Our study reveals that while learning from unknown examples slows down the model's integration of new knowledge, incorporating examples with lower certainty levels enhances the model's performance in handling new information during testing. Section: Quantifying knowledge in LLMs. In this section, we aim to evaluate the impact of introducing new knowledge into our model M_D. To do this, we need to label each question-answer pair, Q, A, in the dataset D based on whether our model M knows the correct answer to question Q. We introduce a measure called P_text correct to categorize the Q, A pairs into 4 knowledge groups using a method called SLIC, sampling-based categorization of knowledge. We consider that our model M knows the answer to question Q is A if it generates a when asked about Q. Since our model M is a base model without specific fine-tuning for following instructions, we train it using in-context learning with a few similar examples to question Q. It's important to note that due to the influence of example choices and randomness introduced by temperature sampling, our model may predict different answers. Therefore, we define P_text correct Q, A, M, T to estimate how likely our model is to generate the correct answer A to question Q when given random few-shot examples and using decoding temperature T for our study. We approximate P_text correct using 10 different sets of 4-shot prompts. We predict the most likely answer using T equals 0 and sample 16 answers using T equals 0.5. The fraction of correct answers with T equals 0 represents P_text correct Q A M T equals O, while the fraction of correct sampled answers with T greater than 0 represents P_text correct Q A M T greater than O. We then categorize the knowledge levels based on the P_text correct values. The unknown category includes pairs where our model never predicts the correct answer. If our model sometimes predicts the correct answer, we classify the pair as known. Within the known category, we further divide the pairs into highly known, always predicted correctly, maybe known, sometimes predicted correctly, and weakly known, never predicted correctly. By applying SLIC, we label each Q/A pair in our dataset with its corresponding knowledge category. We will assess the effectiveness of these categories in the following section. Section Summary. In this section, we quantify knowledge in language model, LLMs, by categorizing Q/A pairs based on the model's ability to predict the correct answer A to question Q. We introduce the SLIC approach to classify pairs into 4 knowledge categories: math unknown, math known, math highly known, math maybe known, and math weakly known, based on the model's prediction accuracy. By analyzing the impact of new knowledge in the fine-tuning dataset D on model performance, we manipulate the proportion of math unknown examples in D while keeping other factors constant, shedding light on the model's ability to generalize and avoid hallucinations during testing. Section Fig. Fixed_steps_plot presents the performance as a function of the percent of $math unknown $examples in $D for different fine-tuning durations. Higher percent $math unknown leads to performance degradation, regardless of the fine-tuning duration, which indicates that $math unknown examples are less useful than $math known Performance is also strongly affected by the fine-tuning duration, with early_stop typically yielding the best performance. Training for more epochs usually reduces performance, with the lowest performance observed for convergence, which can be attributed to overfitting $D. Interestingly, this effect increases with larger $percent $math unknown The interline spacing from early_stop exhibits a monotonic increase along the positive x-axis, suggesting that a higher percent $math unknown increases the risk of overfitting. In this section, we observed that a higher percentage of unknown examples leads to a decrease in performance, regardless of how long we fine-tune the model. This suggests that unknown examples are not as helpful as known examples. The duration of fine-tuning also greatly affects performance, with early stopping usually resulting in the best performance. Training for more epochs often leads to lower performance, especially when the model starts to overfit the data, as seen in the convergence stage. We were curious whether unknown examples are harmful or have a neutral impact on performance. To investigate this, we removed all unknown examples from the dataset and only kept the known ones to create a new dataset. Surprisingly, for the early stopping scenario, the performance with the original dataset was almost the same as with the modified dataset containing only known examples. This suggests that unknown examples had a neutral effect on performance in this case. However, for the convergence scenario, removing unknown examples significantly improved performance, indicating that they were actually harmful in this case. We also found that unknown examples are fitted by the model at a slower rate compared to known examples, especially in the early stopping phase. This slower fitting rate for unknown examples may explain why they have a negative impact on performance in later stages of training. It seems that the model struggles to learn new information from unknown examples and mainly relies on the known examples to improve its performance. After the early stopping phase, as the model starts fitting more unknown examples, the performance tends to deteriorate. We aim to analyze this relationship more precisely by using a linear regression model to understand how fitting known and unknown examples influences test accuracy. The results showed a strong linear relationship between the type of training examples fitted and test accuracy. Fitting unknown examples had a negative impact on performance, while fitting known examples had a positive impact. The negative impact from unknown examples was comparable to the positive impact from known examples. Section Summary. In this section, we find that a higher percentage of unknown examples leads to performance degradation during fine-tuning, with early stopping typically yielding the best performance. By filtering out unknown examples, we observe that they can be harmful, especially during longer training, as they contribute to overfitting. Additionally, our analysis shows that fitting unknown examples significantly slower than known examples can impact the learning process of language models, suggesting a struggle to acquire new factual knowledge through fine-tuning. Section: Generalization to new relations. In this section, we generalize our findings to new relations. We explore if the dynamics we observed in our model's knowledge transfer to relations not originally in the dataset. To test this, we set aside some relations for an out-of-distribution (OOD) test, keeping them out of the training and development sets. Our results on the OOD test show that a higher ratio of unknown examples leads to lower performance, and unknown examples can harm performance, especially when the model fits them well. A linear model of the OOD test accuracy confirms these trends. Overall, our insights apply to different relations, indicating that fine-tuning on unknown examples can lead to incorrect answers on unrelated questions. When studying the impact of unknown fine-tuning examples, we grouped known categories together for simplicity. We then analyzed how training examples from each category affect test performance and how the model performs on test examples from each category. We created datasets focusing on single categories and observed that fine-tuning on maybe-known examples is crucial for the model to handle such examples accurately during inference. We found that unknown and weakly known fine-tuning examples increase the risk of overfitting. Weakly known examples show a lesser but still significant impact on overfitting compared to unknown examples. Maybe-known examples are essential for improving the model's performance without compromising its handling of highly known examples. These results highlight the importance of selecting the right fine-tuning examples to enhance the model's performance and prevent overfitting. Section Summary. In this section, we explore the generalization of our observed dynamics to relations not represented in the training data. By reserving a subset of relations for an out-of-distribution test set, we find that fine-tuning on unknown examples can lead to hallucinations on unrelated questions, indicating the model's tendency to generate answers not grounded in its existing knowledge. Additionally, we discover that fine-tuning on maybe-known examples is crucial for the model to handle such cases accurately during inference, showcasing the importance of selecting appropriate fine-tuning examples to enhance the model's performance and prevent overfitting. Section: Slick Knowledge Categories Analysis. In this section, we proposed a classification system called SLIC to evaluate a model's knowledge across 4 categories. We analyzed the effectiveness of our classification by examining how well the model performed on different levels of known facts. We found that our classification system was able to distinguish between highly known facts, moderately known facts, weakly known facts, and completely unknown facts. When testing the model on unknown facts, we observed that its accuracy was very low, indicating that the model struggled with these types of facts. We compared our approach to another method called P-True, and found that our classification system was better at identifying unknown examples that the model had difficulty with after fine-tuning. Our study also revealed the risks associated with fine-tuning models, as it can lead to the model generating incorrect information based on its existing knowledge. We suggested that filtering out unknown examples during fine-tuning could help prevent overfitting and improve performance. Additionally, we explored the idea of relabeling unknown examples with expressions of uncertainty to see if this approach could be more effective. We discussed the superficial alignment hypothesis, which suggests that models primarily learn during pre-training and only adapt their style during fine-tuning. Our research indicated that fine-tuning on highly known examples did not always lead to optimal performance, highlighting the importance of selecting appropriate examples for fine-tuning to enhance the model's ability to utilize its existing knowledge effectively. Section Summary. In this section, we proposed SLIC, a 4-category classification system to assess a model's knowledge. We found that categorizing facts into highly known, maybe known, weakly known, and unknown can provide valuable insights into a model's understanding. Our analysis revealed that fine-tuning on unknown examples can lead to overfitting, emphasizing the importance of early stopping and aligning fine-tuning data with the model's existing knowledge to improve performance and reduce risks of hallucinations. Section: New Knowledge and Hallucinations. In this section, we explored the relationship between new knowledge and hallucinations. We discussed the idea that fine-tuning models with new factual information could potentially lead to hallucinations. We classified the causes of hallucinations and formally termed this situation as capability misalignment. It was noted that there is limited research on capability misalignment because defining the knowledge boundaries of large language models, LLMs, is challenging. Our study revealed that when a fine-tuned LLM faces unfamiliar queries during testing, its responses tend to resemble the responses linked to the unfamiliar examples in the fine-tuning data. We also found that LLMs do not perform well when they encounter new information in their input contexts, and we examined the effects of learning from unknown examples within the context. To the best of our knowledge, our research is the first to empirically evaluate how exposing a fine-tuned model to new knowledge through fine-tuning can influence its tendency to produce hallucinations. We also discussed quantifying knowledge in LLMs. SLIC was introduced as a method to elicit confidence in the ground truth label, indicating that the model knows the answer to a question if it is confident in its response. Previous studies have obtained calibrated confidence from LLMs by assessing agreement across multiple samples, analyzing internal representations, eliciting verbalized probabilities, or directly prompting the model. Additionally, a separate model, P.I.K., was trained to predict whether the LLM knows the answer to a question. The label for P.I.K. was estimated based on the fraction of correct sampled answers, which aligns with the concept of P_text correct. One key distinction is that we defined the SLIC categories and provided evidence that we captured meaningful and useful categories.